So yeah, now let's continue. So now we've introduced our weak solution, and we also partitioned the string or the length, the region we're working on. So to sum up what the new weak solution is, well, we have to sum up the contribution for each of the regions. So first, this is summing up all of the basis functions, Ci. So this is the expression of the solution. And then this one is new, so E goes from 1 to NE, so the element. And then this integral is only over this GE region. Rho x Cj of x, Ci of x dx. Then we have to add all of these. 1 to n Ci of t. That is sum over all the regions. And then E. And then the integral nu x dx psi j x dx psi I of x dx. And then this should give us our source term. Again, sum all the partitions or regions or smaller regions GE psi j of x xt dx. So in this expression we'll have that the Cj, this is the test function, and Ci, this is the basis functions that we use to approximate this u. Func independent of time. And then ui, these are time-dependent expansion coefficients. Time dep exp. Yeah. Time-dependent expansion coefficients. TDEC. TDEC, maybe? So the challenge is to actually find these time dependent. So just to make a clear point of 2. So you have to find these, you need a solution for all of the elements, all of the partitions, for all of the elements. So the solution to do this is to choose these basis functions, so these that only have local support on some of the elements, or only one element at a time. And that means that we get different basis functions for each element. So we are going to introduce a lot of basis functions. It's going to sound complicated, but in essence, it's really not. It's just bookkeeping. So we are going to keep our do our bookkeeping in a efficient and good manner. So it's easier to keep track of everything. And then we can have these discrete equations. So if these only have supports on each element, that means that they are 0 for every other region, every other element in the region, each other GE, makes life a lot easier. So let's if we pick these in a good way. Should probably write this up. So we choose basis function well, in or on only one element. Which, if you go back to this model here again, and we have discretized it, that means that each of these basis functions only have support on one of these. So it could, for instance, be like this, and then 0 for everything else. So this basis function I only contributes in this point. So then we can disconnect all of the elements. And since we can just disconnect all the elements, we'll first look at the solution in only one of the elements, meaning that we can sum them together when we're finished. So, we're going to look at the on one element. So for this, we need to define n plus 1 basis functions. So big N call them C, I, E. So this is just numbering. It's not to the power of, it's just a numbering. So this is the basis function C number I, which has support on element E. Nope. And E elements. So we need a lot of these basis functions, but we're just going to focus on one. So I say that we need to define n plus 1 on each of the elements. And then the displacement field. This is basically the U. U within this element GE. Well, it's approximated by something. Oops. By. Just going to go over here. And you've seen this before. X of t and x should now be inside this element GE. Well, then we only need the functions which are inside the element GE. E of t, ci e of t, like so. And then this is going to be basically the same equation as this, but for completeness sake, let's repeat it. Plus 1 and plus 1, ui e of t ge rho at position x c j e x c I e of x dx plus I plus 1 big N plus 1 u I e of t integral. We're also going to solving this integral later. dx c j e of x c I e of x. I forgot these dx partial x then be the local force. C, J, E, X, X, well, X, T, dx. Yep. And then we have a local matrix representation of this. Again, you've seen this before, only without the e's. K, U, E, oh yeah, right. K, E, F, E, T. So yeah, the local mass matrix, the local stiffness matrix, and the local source term vector, I guess we can call it. And then this is done for each of the basis elements. That means that in total we would need, well, here we're using big N plus 1 on this element, and we have NE elements. Each of them have the same amount of basis functions. Total basis functions. Then we also have to make sure that this U is continuous. Since, well, these basis functions, so these basis functions, they only have local support, as I tried to explain down here. In all of the other elements, which is not equal to E, this will be 0. So you have to explicitly ensure that you have a continuity when you use this. So you have to explicitly impose it. So now we have a lot of difficult integrals. Can we do something to make them easier? Can we perhaps introduce some kind of reference element that we compare all of them to? Well, rhetorical question, yes we can. But yeah, you can briefly, just before I take this away, it is basically the same equation, only, well, we've switched the sum a bit. So here we are summing over each of the elements, but we don't have to do that over there because that's only for one element. So you can see, and the over here, this is one element E. And then again, we have to solve this for all of the elements. So then we're going to introduce a so-called reference element. So in 1D, this is going to be simpler, at least. So this is GE. Let's go from A to B. And then we will have our reference element going from -1 to 1 here. No, -1 to +1. I'm going to call this big lambda, capital lambda. So then we have going from GE to here. We're going to call this transformation FE inverse. And then going the other way, this is FE. So this is basically just a stretching. We're just stretching this A, B to fit within -1 to 1. And we have previously used a transformation for this. No, well, a similar transformation when we used the, which basis function were those? It's the same here. Anyway, this Fe is defined to be from -1 to 1 to GE. Yep, and this X is then the, well, I forgot the detail here. So over here we will call the position X, and over here we will call the position Xi. So in order to find where we are, when we look at this, we just perform the transformation and we will get where we are in a non-stretched manner. And then if we want to go the other way, well, then we have the inverse operation. -1 of X. And then, of course, this Fe has to be a bijective function, if you remember again from calculus. So we need to be able to hit every point here just once, and also going back. So basically just finding this is an interpolation problem, and we've solved this before. It is also called a linear mapping, so could be you had it in Math 3 or your linear algebra classes. So this is just an application of this. So I will just have an example of how to do this. So I will introduce. So now this is just to make it a bit easier. I'm going to cut this in half from 0 to 1, and I'll use omega for the GE. From A to B. So now omega is this GE, and lambda, well, this is lambda bar. It's kind of half of this, but this is similar still. So on lambda bar, we want a function of Xi bar to be approximated in the same manner. By so u Xi bar equals something of C1 plus C2 here. Again, this is analogous to the displacement. Well, we also have that at the beginning, U0. You see that's going to be C1, whereas U1, well, C1 plus C2. That is, just insert this in there. So C1 plus C2. Like so. So now we need to find these C1 and C2 in order to find our transformation. Well, this we can do. I mean, we do have two equations and two unknowns already, so why not just use them? So C1, C0, and C2, u of 1 minus u of 0. This means that u of xi bar is, so now I'm just using this, inserting what they are supposed to be. One minus u of 0 psi bar, and we get u of 1 is psi bar. So then we have basis functions in this. So one, well, this is the first one, and two, and then we have everything we need. So now we've covered half of the interval. So now we want to move into the rest of the. So now we want to move from R to the full one. Then we can use the transformation xi bar plus now equals xi plus 1 half. So then we have 1 xi. So now I'm just inserting this, the ones down there. So now this xi bar is this, and then you would get basis functions for this, no, this lambda 2 plus xi, and we have our transfer function. No, just f. This is from going to here to here. A over 2 minus xi plus p. No, sorry, this is from going from omega to this. B over 2 plus. Yeah. So this is basically how we are going from this here to this. So it's going to be different in each of the elements because it's starting at a different point A and ending at a different point B. So you have to keep all of these, all of these FEs. So if I'm going from this to here, can also illustrate it. So this is, we have lambda over here. We have omega or GE. Just F. So it's just a transform, and now we can use this for the basis functions, meaning that the psi dx, well, in the transform space, we need to take care of this. Psi, so I'm dropping the subscript here, but it's for all of them. This again is the chain rule. So yeah, again we have to rebuild our equation using this. So now we're only working on this big lambda. Actually applying the transformation over there. Dot t. So now we actually know our integral, which is from -1 to 1. But we also need to transform all of our model parameters. So for instance, the density. C, J, E, X, J, C, X. This was bad planning on my part. Dx d psi. So this last bit might seem a bit weird, but if you do, well, if I actually do this, let's see, I'll just look at this more. So this construct here, it looks like we just introduced it. This is so we can integrate over the xi space instead of the x space, meaning that we can integrate over the lambda space instead of the GE space, if you want to say it like that instead. But if you have dx and you multiply this with 1, well, what can 1 be? That can be dxi over dxi, and we get dx over dxi, and this is going to be dependent on the transformation dxi. So this is the integrating variable right now. So this one is connected to the integral from -1 to 1. And then this one is dependent on transformation. But that's only the first term. So apologies for making it. This is the first term. We're going to plus something up here. Plus 1, I plus 1. U and E, and this is going to be a bit more interesting since we have the derivatives U of C, J, E, xi. Then, well, we're using this. So we need to introduce d over dx squared. That's because we are transforming our basis functions. And then we get the same construct in the end, the xi. So this bit, again, comes from this bit. So the chain rule, basically. We're missing 1 to 1. Minus 1 to 1. J, E. And then f of x, xi, t, dx, dxi, dxi. Yeah. And then, what do we have now? So, sorry for, well, making this weird, but this is the first part. We continue up here, and then this is equal to this. So that this is the weak formulation on each element as transformed to lambda. And then finally we'll start looking at these weird things. So these are called basis functions, as I mentioned too many times now. We're free to choose them as we want, but why not choose a basis that will actually benefit us? So we actually have functions that are easier to work with. Or make the computation is easier. So we're going to using Lagrange polynomials, and we've had this before. So for the basis functions, we choose Lagrange. N plus 1. Of degree n, and they will use some different points than last time. The last time we had Gauss-Legendre point, now we use Gauss-Lobato-Legendre point. Place of degree n. Yep. And Gauss Lobato Legendre or GLL points. So we haven't had these before. We only had the Gauss-Legendre points. The Gauss-Lobato-Legendre points are slightly different. Why do we have them? It's basically just we've decided to have them. Or actually, it's been proven that, they've shown that they are the best points. They are good points to pick. You could just pick random points, but then you would have trouble keeping track of them. Or you could pick the endpoints, but then again you would have a problem with this Runge's phenomena, in the end it would oscillate a lot. So these points ensure a very good accuracy of your routine. Yes. Points, I forgot. So these are the co-location points. It's called. Which is to say that these psi's, Ci of x of psi are these Lagrange polynomials. Yeah, Lagrange, not Legendre. Lagrange. There's a lot of names right now. At psi and xi is between -1 and 1. So these are defined at big lambda. I mean, it is possible to find these Gauss-Lagrange points on all of our GE elements, but they are kind of difficult to find. So why not just compare them to a interval that we know what the points are supposed to be. So these points can then be pre-computed, and you can save a lot of computing time by just looking them up in a table. That is also what I would suggest that you do. So for instance, if you want a polynomial of degree 4, so deg, and these co-location points, well, the polynomial of degree 4 would have 5 co-location points, and they are 0, plus and minus the same of the square root of 21, and plus and minus 1. If you want a polynomial of degree 5, so I would suggest you look these up in a table. I think some of them are listed in the book by Fichtner, which his lectures are based on. Well, I can try to, because, well, these are kind of nice and fine, but when you start increasing the polynomial degree, let's see if I can get this correct. 1 over 21, 7 minus 2 square root of 2, plus minus this, and then plus minus square root of 1 over 21, 7 plus 2 square root of 2, and plus minus 1. So that should be in this book by Andreas Fichtner. It's actually a very good book as well, and it's freely available online. It's also listed in the curriculum. So, to reiterate, we have this thing called Runge's phenomena, which in case you don't remember, is that when you try to approximate something on this interval from A to B, and if you don't use good points, you will get the error would oscillate like a lot around this. So it would introduce a lot of error in the ends of your region. That was not the best drawing, but And also by using this, the numerical errors are so-called minimized. They have been proven to be minimized. We won't go into details. And also, remember that we have an integral here. This thing. We can also use these GLL points to do GLL quadrature. So actually approximate the integral. And you will show that this integral is very easy. So it's the same as this Gaussian quadrature. That we are able to approximate this integral very accurately without introducing too many points. So I think the last thing we'll do is actually inserting these points in the weak formulation. Make sure to have enough space. Yep. So, one and plus one, I, e, double dot of t, then our integral over lambda. Yep. Then rho, I will call this rho bar because it's a slightly transform. Lj of xi, li of xi dx dxi dxi plus the second term plus 1, we need all of the basis functions, which are now Legendre polynomials. Well, lambda mu bar of xi d psi l j of psi d psi I of xi, and then the psi dx squared dx d xi d xi equals integral over lambda L j xi xi t dx d psi d xi. And then for details, this one xi is the transformed density. The transformed elasticity. And then we need the transformed force term. Oops, x of xi of t. And so here I've substituted these. I've also just skipped to write the degree of them, but well, it's the jth Lagrange polynomial. So, does it look? Do you think you'll be able to solve this? Does it look easier now than to begin with? Because now we have these, we're going to easily find them, and this integral, you'll see that they are behaving well. And also the derivative of them, I'll do this on Tuesday. But it's basically just a product of the points. So it looks complicated, but when you start trying to solve it, you'll see that picking these Legendre polynomials as basis functions just makes life a lot easier. And you can skip some sums, and the integrals are just like neat and tidy, and life is good. Math is fun. Well, it is. Any questions? No? Then I wish you good luck on the project.